Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good evening to everyone here.
Waalaikumsalam, Doktor.
Good evening.
Alright. Hi, Tivaga. Alright, 46. Yeah, good evening, Yuan.
Halo. Baik, baik, baik. Baik. Saya tengah mesyuarat. Tolong WhatsApp saya ini tadi pun nanti saya akan call balik. Boleh.
Okay. Section 7. Last Thursday we stopped until first order system. First order or second order last week? Last Thursday.
First order, Doctor.
Alright, okay, first order, thank you. Alright, so for today we're going to continue with second order. Alright. Let me start recording first. Alright. Okay. So let's recap what we have learned about classification, right? Where we said there are three types of classification based on order, based on rank, and based on class. Okay. Then later we said order is the most common method in order to classify a control system. So then we have looked onto first order system. Okay, that is on last Thursday. Right, that is the last topic that we have discussed. So I believe everyone is still remember the transfer function for first order system. Okay, where it is k over 1 plus ts. Okay, so we have discussed about k, the gain, the static gain, and then we also discussed on the effect of t, time constants. All right. So for today we're going to look onto second order system. Okay, we want to see how a second order system will behave and what are the parameters that will describe the behavior of second order system. Okay. All right. So first we start with the general transfer function for a second order system. Right. So we can see here. The transfer function is given k omega n square over s square plus 2 zeta omega n s plus omega n square. Okay, so looking at this transfer function, we can see that there are three parameters which are k. Okay, k is the system gain, which is actually the same as the k in the first order system. Okay, the effect is the same as the k in first order system. Okay, meaning it will amplify the input and it will give the final value. Meaning the relationship is still y. Okay, y equal to k multiplied with u, and y here is at y steady state or y final. All right. Okay, that is for steady state region. Okay. Then in terms of transient response, the behavior at the transient region will be described based on the value of omega n. Okay, omega n is undamped natural frequency. Okay, and then the second parameter is zeta, which is a damping ratio. Right, so these three parameters is actually the parameters that will affect the response of the second order system or the shape of the second order system. Okay, and this parameter is also known as a design parameters. Okay, we need to choose this value in order to produce some response that we want. Okay, meaning we know how we want the system to react. Okay, so we need to choose the value of k, zeta, and omega n so that the system will provide such output. Right? The function of time response. Okay, example of second order system is mass spring damper. Okay, so if you look here, due to the mass here, the equation will be Fs plus Fd equal to md square x. Okay, so it is SI minus S naught. All right, so the important part is actually the d square here. Okay, so if you remember when we derived the time response equation, d square is the second differentiation term. Okay, and if we convert into Laplace, d square will become s square. Okay, so later the s square will be at the denominator of the transfer function. So that's why the transfer function has become a second order system due to the highest order of the denominator is 2. Okay, so for this system, okay, in order to get the time response equation, we will do all the steps again, which is first produce the ODE, second transform the ODE equation into Laplace form, okay, apply the initial condition, apply the input, partial fraction, and then solve for the parameters using Reminder theorem, and then lastly we inverse the Laplace, become YT. So the YT is the equation that will describe the behavior of second order system. Okay, so we're not going to do that. I just recap the step there. So if you want to try to do that, so you need to follow the step there. All right, so basically the time response equation has been derived here. Okay, so it is onto the same system just now. Okay, where we consider k equal to 1. Okay, so the derivation has produced this equation as the time response equation for the second order system. Okay. All right, so here we can see that, okay, okay, you can see 1. Okay, 1 is due to unit step input. All right, and then we can see sine wave. Okay, there will be a sine wave in a second order, meaning there will be a sine wave behavior in the second order system. And then this part here will explain how fast the energy will be damped in the system. Okay. All right, so we have seen the parameter zeta from the transfer function, and also omega n, and then there is additional omega d here. Okay, omega d is damped natural frequency, omega n is undamped natural frequency. Okay, and then we have alpha, which is the phase shift. Okay, this is actually a delay. All right. So we have three parameters, K, omega n, and zeta. Right, so K, we know that the effect is it will increase the input, which is equal to the final output, Y equal to KU, right? So if your input is not a unit step input, maybe your unit is 2, so you can expect the value here will become 2. Okay, and then we have undamped natural frequency. Okay, so we need to know the value for natural frequency because we want to avoid resonance. Okay, we do know that the resonance will occur when we operate any system at the region of natural frequency. Okay, so we need to avoid a region, meaning we need to avoid natural frequency with some margin lah. Okay. All right, and last one is zeta. Zeta is damping ratio. Okay, the function of zeta here is actually to damp the energy in the system. Okay, damp meaning we're going to try to reduce the energy. Okay, so that is the function of zeta. It will reduce the energy, but how fast it will reduce will be based on the term here. Okay, that is the parameter that we explain how fast the energy will be reduced. All right. Okay, so we have the transfer function, and then we have the time response equation. All right. So here we're going to see the effect of damping ratio. I already explained the effect of K and also the effect of natural frequency, right? So damping ratio will very much, the value of damping ratio will affect the behavior of the second order, right? So for example, here we have three type of response, depends on the value of zeta. Okay, so the first response is when we choose zeta bigger than 1. Okay, so we call that as overdamp, meaning when zeta is bigger than 1, we consider that as overdamp, too much damping value in the system, damping energy in the system, right? So in this case, we can see the behavior of a second order will behave like a first order. Okay, it will behave very much like first order system. There will be some delay before it reach the final value, but there will be no overshoot. It will not cross the final value or maybe lower than final value. All right. For the second second behavior is when we choose zeta equal to 0. Okay. So when zeta equal to 0, this is mean that there is no energy that able to damp the energy of the system. Okay. So in this case, the system will oscillate. Okay. It will oscillate and the amplitude of the oscillation will be the same. Okay. So if there is no damping, it will keep moving at the same amplitude over again and again. All right, because there is no energy that able to reduce the energy of the system. Okay, the function to reduce the energy of the system so that we want the amplitude to be reduced over time. Okay, so if there is a damping, okay, maybe a low damping, so we expect to have some reduction. Okay, so that it will slowly reduce the amplitude and then settle at the final value. Okay, but if there is no damping, that behavior will not occur in our system. All right. So last one is the most optimum value that we need, we can choose for zeta, which is we call a damp system, meaning there is damping there, and it is enough, okay, to reduce the energy. Okay, so in order to get a damp system, we can choose a zeta value to be bigger than 0 and lower than 1. Okay, so this is the kind of behavior that we want. So we want, meaning this is a common behavior for second order system. Okay, you can see that if we start from 0, increase to the final value, then it will be overshoot. Okay, it will produce more than what we want, so we call that as overshoot. And then due to the damp element, it will slowly settle to the final value. Okay, so different value will produce different response. Okay, so maybe you can see a response like this. Higher overshoot but faster settlement. Okay, you can see the overshoot is bigger. Okay, but it settle faster. Okay, or maybe your system require lower, but it will take longer time to settle. Right? But of course, meaning the specification of the system is based on our requirement, how we want our system to behave. Okay, some of system will require faster settling time. Okay, meaning you want the system to settle faster to the final value. Okay, but it doesn't matter if the overshoot is higher. Okay, maybe like this. All right, it doesn't matter the overshoot is higher, but as long as we can settle to the final value faster. Or some system maybe require a small overshoot, okay, due to the limitation of the system. Okay, the system cannot exceed some of the value, so it require small limitation. But it is okay if it take longer time to settle. Okay, so the requirement will be based on the system. Okay, the designer of the system will know kind of behavior that they want from second order system. Okay, so the value of zeta and omega n will affect this value, the maximum overshoot, the rise time, the settling time, and etc. Okay. All right. So when we discuss first order system, we said the time constant will explain how fast the response of the system. Okay, and the k value will determine the final value. Okay, so in second order system, we have three indicators that we want to have, study in a second order system. Okay, the first one is how fast the system responds toward an input. Okay, if for the first order, we consider the time constant. Okay, we consider time constant is the time taken to reach 63.2% of the final value. All right, but in the case of second order system, we consider the rise time. Okay, the rise time will explain how fast the system responds to an output. And the rise time, sometimes we use 0 to 100, meaning time to reach 100% of the final value. Or sometimes there is also condition where we could just consider 90%. Okay, time taken to reach 90%, right? It's different from first order. First order is time taken to reach 63.2%, right? For the first order, commonly we check for 0 to 100, okay, but there's other condition 0 to 90. All right, that is the parameter. All right, the second indicator that we want to look is how is the how much oscillation in the system. Okay, meaning how much oscillation will be produced by the system. Okay, so the oscillation will be explained by the parameter of MP, T1, T2, T1, T2. Okay, so MP here is the this one here, the difference between the highest point minus the expected point, which is 1. Okay, so the difference of the peak, highest peak minus the final value 1. Okay, and then T1 is the time taken to reach peak number 1. Okay, so T1 is this one here. Okay, rise time T1, and then T2 for peak number 2. If there is peak number 3 and you want to study about peak number 3, then you calculate for T3 also. Okay. All right, and last one is the parameter that explain how long does the system takes to reach the final value. Okay, so the parameter for this one is settling time. Settling time. Okay, TS. Right, so which given by this one here, settling time, TS. So settling time is considered as a time taken to the system to reach the final value. Okay, so the final value is considered, you can see the 2% here. Okay, so that is the range that define the final value. Okay, some we can use 2%, but there is also use 3, 4, and 5%. Okay, so it can exceed 2% between the final value. Okay, so if, for example, if it is 1, so the 2% is 0.9 and 1.1. Right? So if the system reaches 0.9, so it will consider the system to, meaning if the vibration is in the region of 2%, okay, meaning the output is within 2%, it changing, it increase, decrease, but still within 2%, so we consider the system has reached the final value. Okay. All right. So that is the indicator that we look, meaning by calculating the parameter of rise time, maximum overshoot, T1, T2, settling time, we'll be able to explain the behavior of the system. Okay, we can compare a system based on how fast it reached the final value, rise time. Okay, we can compare based on a maximum overshoot. We can compare based on the settling time. All right, so this is the equation to calculate rise time. Okay. Right, all the parameter has a equation in order to calculate that. So this is for rise time. Okay, pi minus tangent inverse 1 minus zeta square over square divided by omega d. Right, this is the equation for peak time. Okay, T1 is pi, you can simplify pi over omega d. Okay, T2 is 3 pi over omega d. T3 is 5 pi over omega d. Right? Right, and then we have maximum overshoot. Maximum overshoot is the difference between first peak and the steady state value in percentage. Okay, so you need to understand it is the okay, so it is the MP that we calculate using this equation here is actually the difference between the first peak and the steady state value or final value. Right, and then the last parameter is to calculate the settling time. Okay, so this is the general equation. Okay, so maybe if your system allow up until 3%, okay, you put that 3%, and then you can calculate for TS. So TS here is the settling time. Provided you have the value for zeta and omega n. Right? But the most common percentage that we use is 2%. So if the limit is 2%, then we can just use the equation here. TS is approximately equal to 4 over zeta omega n. Alright. Okay, the last one is just the equation for omega d. Okay. Any questions so far? Any question? No.
No.
All right. All right, let's look on to the example. Okay, example number 1 is given a transfer function of second order system, right? So we need to determine the gain, which is K, omega n, and zeta, right? So we can do that by comparing the transfer function of a system to the general transfer function of second order system. Okay, so we're going to compare to K omega n square divided by S square plus 3S plus 9. Right, the first step is to compare S square. Okay, so you have to make sure that the transfer function is written in S square. Okay, we cannot have 3S square. Okay, the constant for S square must be 1. Okay, if it is 3S square, you need to divide all this by 3. Okay, because we want to make sure that the parameter for S square is 1. Okay, because the general transfer function have 1S square. Okay, not 3S square, not 10S square. All right, so since it's already in S square, so therefore we can compare term by term. Okay, so we can compare this one is equal to 18. Right? 3 is equal to 3 kat situ. 2 zeta omega n. Macam mana saya tulis ni? Salah ni. Okay, the general transfer function is S square plus 2 zeta omega n S plus omega n square. Right? Then only we can compare that. Alright, so here we have K omega n square is equal to 18. Right? And then by comparing 2 zeta omega n is equal to 3. Right? And then we are also comparing omega n square is equal to 9. Okay, so we have 3 equation, 3 unknown. We should be able to solve that. Okay, so therefore omega n is equal to 3 radian per second. All right, and then from the equation here, we have 3 multiplied by omega square. 9 lah. Therefore, K is 2. Right, and last one is zeta is equal to 3 divided by 2 divided by 3. Okay, so it will give us 0.5. Right, K is again, so there will be no unit, and then zeta is a ratio, then there is also no unit for zeta. Only omega n will have unit radian per second. Right, so in order to determine the parameters K, omega n and zeta, we need to compare the transfer function to the general transfer function. And we need to make sure that the transfer function is already written in the general form. Meaning, okay, meaning the s square there. Okay, it cannot be 10s square, it cannot be 2s square, it cannot be 0.5s square. Okay, we have to make sure that it is s square plus something s plus something. Right, that is what we can learn from example number 1. Okay. All right, example number 2. Okay, example number 2 is just for you to use the equation given. Okay. We already look onto the equation. We can see that all the equation will depend on the value of zeta and omega n, whether to calculate the rise time, to calculate maximum overshoot, to calculate T1, T2, and also settling time. Okay. So in this example, the value is given. Okay. Maybe you need to determine from the transfer function, okay, like in the first example. Okay, but here it is already given, so we're just going to put the value into the equation, right? So you just need to remember the equation, right? So it want you to calculate for omega d, T1, T2, and also MP. All right. So refer to the equation. Okay. MP is 3T1. Okay, T1 is pi over omega d. T2 is 3 pi over omega d. And then MP is equal to exponent negative zeta pi divided by square root 1 minus zeta square multiplied with 100. Alright, so we can see that all the parameters will require the value of zeta and omega n. So since we already have the value, then we can just put into the equation and calculate for the values. Alright. Okay, I will just let you to calculate that because it's just direct calculation. Alright, example 3. All right, in example 3 here, it is given a block diagram, right? Meaning we don't have the transfer function. Okay, so you need to determine the transfer function from a block diagram given, or given block diagram. All right, so from the transfer function, you're going to determine the parameters, k, zeta, and omega n. And then from the parameters, you're going to calculate here is percentage of overshoot and settling time. Okay, you need to determine omega n, which is from the transfer function, maximum overshoot, and then settling time. All right, so basically, of course, you need to determine zeta and omega n because all the parameters will require the value of zeta also. All right, so the first step is to produce the transfer function. Produce transfer function from a block diagram. Right, so given this is the block diagram given. Okay. All right. So the basic concept that you have to understand for a time response analysis, it is all the analysis will be based on the closed loop transfer function. Okay, so meaning we need to produce a closed loop transfer function from the block diagram given. Okay, I already explained to you that some analysis will require open loop transfer function, like classification. Okay, last week we discussed on classification. The classification will be based on the open loop transfer function. Okay, so we need to determine open loop transfer function before we do the classification analysis. Okay, as for the time response analysis, okay, any time response analysis, whether it is first order, second order, will always based on the closed loop transfer function. Okay, so therefore we need to determine the closed loop transfer function. So you should be able to do this because the closed loop transfer function is kg over 1 plus kgh. Okay, so we're going to consider this is K, this is G, and this one here is H. Okay, K block, G block, and H block. Right, so putting into the equation, right, let's determine the final transfer function. Right, can you please solve for the closed loop transfer function and then tell me. And consider that K is equal to 20. Okay, this is 20 here. Okay, if you already able to get the transfer function, please tell me the answer. I will let you have some time to solve for that. 2 minutes maybe. All right, anyone?
24 over
24 over
4
4 square.
and 4 plus
4 plus 1.
sekejap. Apa ni?
5.
S plus 1 okay. And multiply with
S square berapa?
0.2s S square.
Soft kan lah. Total kan.
Oh, katakan ingat bagi question ni.
Bagi yang final je. S square plus berapa S? Plus 5 I think. Okay, siapa tu? Christina? Mana ni tak nampak ni. Okay. 0.2 S square plus 1.2 S. Alright. Okay, thank you, Christina. Right. Okay, so that will be the transfer function, the closed loop transfer function from the block diagram. Okay. Alright, the second step is to determine K omega n zeta from closed loop transfer function. Alright. Right, so we need to determine the parameters, which is k, zeta, and omega n from the transfer function that you produce from the block diagram. All right, but remember that you need to make sure that the transfer function is in the form of S square. Okay, so look at here that here we have 0.2 S square. Okay, so in order to make sure it is written in the general transfer function, so we're going to divide with 0.2 divided by 0.2 divided by 0.2. Okay, so please divide with 0.2. It will give you okay, 24 divided by 0.2 is
120.
okay, 120. S square plus berapa S?
6.
1.2 divided by 0.2 is 6 plus 5 divided by 0.25.
25.
Right? So then now the transfer function is already in the standard form. Okay, we can see here it is 1 S square. Right? So we can compare. So we can by comparing there you can have k omega n square is equal to 120. Then 2 zeta omega n equal to 6 and omega n square is equal to 25. Okay, so we get omega n is 5 radian per second. Right. And then k omega n is 120 divided by 25. Okay, berapa value zeta and k?
K 4.8.
Okay, 4.8 zeta
0.6.
0.6. Okay, so now we have all the parameters k, zeta, and omega n. All right. Now step number 3 is right. Okay, we need to calculate for maximum overshoot and settling time. Okay, so this is just putting into the equation. So you need to remember the equation. Maximum overshoot is exponent negative zeta pi over square root 1 minus zeta square multiplied with 100. Okay, and then for the settling time, it is 4 divided by zeta omega n. Okay, since you have all zeta and omega n, you should be able to calculate for this parameter. Okay, anyone? Settling
Zero.
time?
Zero.
Settling time or maximum overshoot?
Maximum overshoot.
Okay, 0.
Sorry, yeah. 9.478%.
Percent.
Uh,
9.47%. Settling time? 4 divided by 0.6 divided by 5.
1.333333.
Alright, so the maximum overshoot is 9.47% or 0.09. Okay, 0.095, you can consider that. Right, and then if we settle to the final value after 1.33 seconds. Alright, okay, so you can see the flow. Okay, if the transfer function is not given, you need to determine the transfer function, but please make sure that you determine the closed loop transfer function. Alright, that is first step. Alright, second step is to determine the parameters. Okay, here in order to determine the parameters, you need to make sure that your transfer function is written in standard form. Okay, and then the last one is just to calculate the parameters. So here you need to remember the equation lah. Okay. Okay. Okay, last one here. Okay. Example number 4. Okay. So the flow is reverse. Okay. In this example number 4, it gives a specification for the indicator lah, like overshoot and the settling time. Okay, and then you need to determine the parameter which is K and P here, which is in the closed loop transfer function, right? So the flow is reverse. Okay, now okay, now this value is given. Okay, give you this value. Okay, so you need to work backward lah. Okay, from the from the value here, we're going to determine the value zeta and also omega n. Alright, and then from omega n, we're going to form the closed loop transfer function. Okay, and then from the closed loop transfer function, we're going to compare with the transfer function of the system where we can determine the value of K and P. Okay, so the flow is reverse. Right, let's do that. Okay, step number 1 is to determine the parameters, which is zeta and omega n. So that will be based on the specification given. So we have the first one is overshoot less than 5% and settling time less than 4 seconds. So you're going to have exponent, maximum overshoot is exponent negative zeta pi divided by square root 1 minus zeta square will be equal to 0.05. Okay, because I not we cancel the percent there, so divide by 100, so it becomes 0.05. Not equal, should be less, right? So it should be less here. And then the second one is we have 4 divided by zeta omega n should be less than 4 seconds. Okay. So here we have two equation and two parameters. Okay, we need to determine zeta m again with two equation. Okay, we should be able to solve that. All right, but if you look onto the maximum overshoot here, okay, the maximum overshoot is only depend on the zeta. Okay, meaning there is only one unknown there, only zeta. Okay, so meaning we can solve for zeta based on the equation here, the first equation. All right. So you're just going to do this. Okay, ln is used to cancel the exponent. Right, it will left you to negative zeta pi over square root 1 minus zeta square should be less than ln 0.05. Okay, what will be the value? Ln 0.05.
52.996.
52?
Negative 2.
Negative 2.99. Okay. All right. Then we're going to square this. Okay, because we want to cancel the square root there. Okay. So we're going to have zeta square pi square should be less than you need to multiply apa tu 2.99 square. Okay, and then you're going to multiply with 1 minus zeta square. Berapa? 2.99 square? 2.996 square?
8.94.
8.94. Alright. So then what is pi square? 3.42 square? 3.142. 3.41. 3.1.
9.87.
9.87 zeta square plus 8.94 zeta square should be less than 8.94. Okay, so then you should get for zeta. Anyone get the value for zeta? 0.
0.69.
69. Right? Yes, it's correct. Right, so meaning in order to have maximum overshoot less than 5%, we need to choose a value of zeta less than 0.69. Okay. All right, then we replace the zeta here. So we have omega n should be bigger than 4 divided by 4 multiplied with 0.69. Okay, so you get omega n should be bigger than 1.45. Right. Right, so we determine the parameters, right? Then we're going to compare to the closed loop transfer function, right? So if you produce the closed loop transfer function, okay, closed loop transfer function from the block diagram. All right, you should get K over S square plus PS plus K. Okay. And it should be equal to K zeta omega n. K, let's not use K here because K is already used. Let me replace with, what is the suitable parameter? Let me use B. It's actually K represent the static gain, but since K is already in the system, let's choose another. Let's choose B, represent for static gain. Okay. Omega n square, which is 1.45 square, divide by s square plus 2 multiplied with zeta 0.69 multiplied with 1.45 s plus 1.45 square. Okay, so basically we can determine K is actually 1.45 square. Okay, this part here. And then P is equal to 2 multiplied with 0.69 multiplied with 1.45. Okay. So you should be able to calculate for K and P there. And then you can also determine for B. Sometimes we don't need to determine for B, but in order to show the difference between K and the static gain, so I let you to calculate B, where we consider B is a static gain. Okay, I believe B is actually 1. K is berapa? 1.45 square. And P is
2.1.
2.1. And K is P is
2.
Okay. So that's how we design a system. Okay, meaning here we need to choose the value for K and P. So it is actually a design step there. Okay, so how to choose that? It will be based on the requirement of the system. Okay, it's given that the maximum overshoot should not less than 5%, and then the settling time should not less than 4 seconds. Okay, pelik pula kan, apa yang less. Apalah, dia punya requirement kan, tak kisahlah tu. Alright, so by doing this step here, we'll be able to design for value of K. So this is basically you need to put less K should not be less lah kot, or equal, tak pastilah, sebab zeta is bigger, zeta is smaller, the range is 0.69 and higher, and then omega n zeta is 0.69 and lower, okay, lower than 0.69, and omega n is must be bigger than 1.45. Okay. All right. Okay, any question? Okay, that's all for the second order system. All right, so it's for 5 o'clock. Okay, I think we stop here. All right, we still have 2 parts for the chapter 2 here, which is steady state error and also controller, effect of controller, feedback controller. Okay, we're going to discuss that tomorrow morning. Right, so for now, I will stop here. Assalamualaikum warahmatullahi wabarakatuh. Thank you.
Waalaikumsalam. Thank you, Doktor.